Hello, uh, good evening everyone. So this is week 5 of the course NOC 24 MA 29 Introduction to Rings and Fields. My name is Pawan Kumar Raikwade and I will be explaining some concepts and solving some problems related to the contents of week 5 that will help you understand the concept better and solve the assignment problems. Okay? So let's start. So let's start with let R1 and R2 be commutative rings with unity. I'll write this abbreviation as CRU for commutative rings with unity. If R1 and R2 are commutative rings with unity, and yeah, so we know the ring R equals to R1 cross R2 is a ring with pointwise addition and multiplication. Not just ring, in fact, this is also a commutative ring with unity with pointwise addition and multiplication. Okay. So now the question is, how are the ideals of R1 plus R2 look like? Yeah. So the proposition says every ideal I of R1 cross R2 is of the form I1 cross I2, where I1 is an ideal of R1 and I2 is an ideal of R2. Okay, so basically you can directly say what are the ideals of I1 cross I2 given the information of ideals of R1 and R2. Okay. So, proof. So this proof we have started for the in the last week itself, but couldn't complete because of some minor details were missing. So now I'll give a nice and precise proof. So define I1 as collection of all elements A belongs to sorry not R1 such that there exists an element B belongs to R2 for which the pair A comma B is an element of I. Yeah. So basically you have I is a subset of R1 cross R2, right? So it will have a pair, some pairs I comma B's where I belongs to R1, B belongs to R2. So I'll collecting the first components basically. All elements, all the first components of elements in I. Basically that's my I1. And similarly, I'll define I2 as collection of all second components of elements in I. The will be in R2 such that there exists an element A R1 for which the pair A comma B belongs to I. That's all. This is my set I1 and I2. So the claim is I is same as I1 cross I2. Okay. So first direction, I is of course contained in I. Yes, I'll write it like this. First claim. Let an element A, since I here, right? A comma B belongs to I, right? So what is the definition of I1 and I2? A is an element such that there exists another element B for which A comma B belongs to I. This will imply A belongs to I1 and B belongs to I2 by definition only. But then this will imply A comma B will belongs to. So this one-sided proof is very trivial. It follows directly. Second side, I contains I1 cross I2. Now let two elements A belongs to I1 and B belongs to I2. Okay, so this implies there exists element B prime belongs to R2 and A prime belongs to R1. Mm, yeah, such that A comma B prime is in I by definition of I1 and A prime comma B is in I. Okay, you have this thing. Now what happens is, since I is an ideal, okay, and 1 comma 0 is a ring element R1 cross R2 times A comma B prime should also belongs to I, right? What is this? This implies A comma 0 belongs to I, right? Similarly, 0 comma 1 times A prime comma B also should belongs to I. Since I is an ideal, so closed under multiplication with elements of ring. So this will imply 0 comma B should belongs to I, right? So this is 1, this is 2, and I is of course a subring being an ideal. This will imply A0 plus 0B. That's all, right? So I have shown that I is precisely I1 cross I2. Okay? Now, now we will show that this I1 and I2 are ideals, in fact. Okay? So now this claim is that I1 is an ideal in R1. So A, let's take two elements. A comma B belongs to I1. So what this implies, there exists element. Okay, what should I name? A1 comma A2. There exists elements B1 comma B2 belongs to R2, such that A comma B1 and A2 comma B2, these two elements belongs to I by definition of I1, right? But what this will imply? This implies A1 plus A2 comma B1 plus B2 belongs to I. R is a ring and this element is in R. So by definition A1 plus A2 belongs to I1. So this is clear that A1 plus A2 I1 is closed under addition. Now take any element. This will imply RA. Uh, what you do is R comma 1 you multiply it with your element A comma what B. Yeah, of your A. Okay, write properly. Now let A belongs to I1 and R belongs to R1. So since A is in I1, there exists B belongs to R2 such that A comma B belongs to I. Now take R comma 0. Hence R comma 0 or this is R comma 1, let's say, times A comma B belongs to I. But this implies RA comma B belongs to I, which implies RA belongs to I1. That's all. So for any element A in I1 and we take a ring element I, the product is also in I1. Hence I1 is an ideal. So exact same lines will follow for I2 to show that I2 is also an ideal. Okay. So I'll the proof. Same. Okay, so now the next thing, let R be a commutative ring with unity and I, subset of R, be an ideal. Okay. Define a radical ideal or rad of I is a set of all elements R in I such that there exists n belongs to natural number for which R power n is in I. Okay. Okay, this is called rad I. This is radical of ideal I. So prove that and second, so if you want to find nil radical, okay, what is a nil radical? Nil radical is collection of all nilpotent elements in R. Okay, nil radical of R denoted by this notion, weird notion. It's hard to draw. It's same as, so like this, nil radical of R quotient I is same as rad I upon I. Yes. Okay, so we have to show these things. So first thing is we have to show that rad I is indeed an ideal. So let A comma B belongs to rad I. So what this implies, there exist element integers n comma m such that A power n is in I and B power m is in I. Okay. So I want to show that A plus B as again belongs to rad I. So what do I do is choose P belongs to natural number such that P is strictly greater than 2 times maximum of n comma n. See why I am doing this is, if I now expand A plus B whole power P, I get summation P C I A power I and B power P minus I, right? I going from 0 to P, right? So in this expansion, what happens is, for each I belongs to this 1 to P, either I will be greater than maximum of n comma m or p minus I. Why? Because if say if I is also less equal maximum of n comma m and p minus I is also less equal maximum of n comma m, then what do you get? The summation I plus p minus I, which is p, is also is less equal 2 times maximum of n comma m. But this is contradiction, right? Since I have assumed p to be greater than 2 times maximum n comma m. Hence this can't happen. So for each I you have this thing. Okay? Which is very useful now, because for each I your either AI belongs to, hence this implies for each I either AI will belongs to your I is the ideal, right? Yeah. AI will belongs to I or b raised to p minus I belongs to I, depending on which one is greater here. Okay. But now then, since I is an ideal, you get a plus b whole power p belongs to I, because it's just the summation of elements in I. Okay. And it's true. So we found natural number p for which a plus b raised to p again belongs to I. This will imply a plus b belongs to rad I. Okay, so now we have to show the multiplication. Now take any R belongs to a ring I and A belongs to rad I. There exists n belongs to with A power n in I. Okay. And R A power n, since you have a commutative ring, this is R power n, A power n. Since A power n is an element of I, you multiply it with any ring element that will again belongs to I. This will imply R belongs to I. Okay. So this is clear. This implies rad I is an ideal containing I, because of course for any I element it's there in rad I, right? Because A power 1 is in I. Right? So I have showed that rad I is an ideal containing I. Now part B is I have to show that nil radical of R quotient I is same as rad I quotient I. Okay. So what is rad I quotient I? This is collection of all R plus I such that R belongs to radical ideal. Okay, so naturally this is subset of R quotient I. Okay, I have to show this is the all this is these are precisely collection of all nilpotent elements. Okay. So take R plus I element belongs to R quotient I. So see the sequences now. If there exists n, okay, I'll write accordingly. There exists n belongs to natural number such that R plus I power n equals to 0. What is 0 in the ring R quotient I? It is I, right? This happens if and only if R power n plus I equals to I, if and only if R power n belongs to I, if and only if R belongs to rad I. Correct? So every nilpotent element, if R plus I is a nilpotent element, then R belongs to rad I. So what this means? This implies R plus I belongs to rad I quotient. That's all. So I have showed that every nilpotent elements are precisely in rad I quotient I. Okay. This part B was very trivial, easy. Now, next question. So, and first of all, this is definition. An ideal I of commutative ring with unity R is called radical ideal if rad I is same as I. Okay. So then the question is, prove that every prime ideal of R is a radical ideal, and second, 0, I mean this is the zero ring, is radical ideal in Z quotient NZ if and only if N is a product of distinct primes. Okay, let's see the proof. So part A, so let A be a prime ideal let R belongs to rad I. This implies R power n belongs to I for some n belongs to natural number. So I can write R power n as R times R power n minus 1. Since I is prime, you get R belongs to I, or you get R power n minus 1 belongs to I. Right? So if R belongs to I, we are done. If then again you can write this as I. This will again imply R power n minus 2 belongs to I. And you keep doing this again, this will imply R power n minus. So ultimately you end up in I, right? That means if R belongs to radical ideal of I, this implies R belongs to I. Hence, okay. So every prime ideal is indeed a radical ideal. Okay. Now the question is you have to find singleton 0 is radical ideal if and only if n is a product of distinct primes. Okay. So what is 0? Okay, let's see what is a radical ideal of 0. Yeah. So this is collection of all elements R in your ring z quotient nz, or any ring, for any ring R, basically for any ring R, radical ideal of 0 is collection of all elements for which such that there exists n belongs to natural number for which r power n is 0. It belongs to ideal generated by 0 means what? 0. So what is this basically? For if this is happening, then R is called a nilpotent elements, right? So this is basically nil radical of R, right? So radical ideal of 0, so I mean radical ideal of 0 is nil radical of R. Now in part 2, what I want to show is this one, this statement. So what is, so if 0 is radical ideal, that means claim is that there are no nilpotent elements. If and only if n is product of distinct lines. Right? But we saw earlier the nil radical of z quotient nz is same as a radical ideal of nz divided by nz, right? So I want to show this is singleton 0, but this happens if and only if radical ideal of nz is same as nz. Okay, so what does this imply? This implies if, so this is if and only if, like r power n belongs to nz should imply r belongs to nz. So what does this mean? This means n divides r power n should imply n divides r. That's all. So when does this happen? Okay, so suppose n is written as product prime factorization p1 raised to what, let's say alpha 1 up to p k raised to alpha k, with alpha 1 positive greater than 1, basically strictly greater than 1, right? Then what you do is you consider r as p1 times p2 raised to alpha 2 rest all as it is, then n will divide r power alpha 1, but n won't divide r because r is a smaller element, right? So hence what follows is from this equation that if there exists any power of pi greater than 1, then this statement will not hold, right? This one. That means we need that this implies n has to be, this implies all Ri has to be 1. For all 1 this equal R is equal to. That's all. Then we have proved this implies n is a product of distinct line. Okay, so I have proved that ideal generated by 0 is is radical ideal in z quotient nz if and only if n is a product of prime. Okay, so what next? So the next concept is the Jacobson ideal. Okay, so let I be an ideal of a commutative ring with unity R. Define Jack I to be the intersection of all maximal ideals of R that contains I. Basically, as we know, we have seen previously existence of maximal ideals. For every proper ideal, there exists a maximal ideal containing I, right? So what you want to find is the smallest maximal ideal which contains I. This is your Jack I. Jack I is a smallest maximal ideal containing I. No, sorry, it's not a maximal ideal. Just the smallest. Yeah, this is how it's defined. It is the intersection of all maximal ideals that contains I. So the convention is do Jack of R as R. Okay. So prove that following. Prove that Jack I So prove that Jaka is an ideal containing I. Okay. So how to prove this? Proof. Yeah. Now second thing. Second, you have to show that radical ideal of I is contained in Jack of I. Okay. And then you have to find for n strictly greater than n, describe Jack of nz. Okay, there are three questions. So the one is easy. I'll leave it to you as an exercise. Since intersection of all ideals is again an ideal and everyone contains I, so Jack I will also contain I. So it is very straightforward. So B also. So what it is? Suppose R belongs to rad I, right? This implies there exists n such that R power n will belongs to I, which is contained in Jack I, right? So this means R power n belongs to is this means what? So for every maximal ideal I tilde containing I, what this means? This means R. Uh, See now, since every maximal ideal is prime ideal, and I have showed before that prime ideals are radical ideals, right? This implies R belongs to I tilde for every maximal ideal I tilde containing I. Hence, R belongs to the intersection which is Jack I. That's all. So I started with an element in rad I ended up in Jack I. This implies rad I is contained in Jack I. Okay. Now part C, I want to find jack of NZ. See, now here we do some analysis now. Take any uh, n, nz. Let's say you're taking 4z, right? So what is 4z? Multiples of 4, right? And you consider 2z. What are 2z? They are multiples of 2. So which one contains the other, right? Every multiple of 4 is of course a multiple of 2, right? So 4z is contained in 2. And you observe here that 2 divides 4, right? So this is in fact not a coincidence. It is always true that nz is contained in mz if and only if m divides n, right? So now if you consider I as nz, then if and any, yeah, okay, yeah, from this also what we can say is maximal if and only if m is prime, right? Otherwise there exists a proper ideal which contains mz, right? Is prime number. And if let I tilde is a maximal ideal containing nz, that is nz is contained in pz, then what we know that p divides n, right? So basically if I collect all the maximal ideals containing nz, then what I'm collecting? I'm collecting all the pz's where p is a prime divisor of n. That's all, right? Perfect. So basically nz, if I now write jack of nz, this is intersection of all pz's, right? Where p is prime and p divides n. But this is basically what? P1, P2 up to Pk times Z. Okay, I'll explain this. So let's say let's say you have distinct primes 2z, you have 2z and you have 3z intersection. What do you get? So this is all integers which are multiple of 2, and this is all integers which are multiple of 3. So their intersection is the elements which are multiple of 2 and 3 both. That means it is multiple of 6, right? So for any distinct primes, basically if you curve P1Z intersection with P2Z, you go on with intersection with PKZ. If PI's are prime, then this is equals to P1, P2 up to PKZ, where PI's are distinct primes. Hence, jack of NZ is Z, where n, the prime factorization of n is like this. That's all. So I can find intersection of all maximal ideals containing nz by this way. Okay. I hope this is clear. So now we'll start the next concept. So next we will start Euclidean domains. So first thing is, let R be a commutative ring we define the concept of a norm. Okay? A norm on R is a function n from R to natural numbers. Okay, yeah, but not just a function with a property such that 0 should go to 0. That's all. So any function from your ring to natural numbers with okay, not just natural numbers, then you have to do natural numbers union singleton 0, right? So any function from your ring to natural numbers union 0 with n 0 is 0 is called a norm on R. Okay. Now we give definition of what an integral domain is, what a Euclidean domain is. First of all, it has to be an integral domain. Okay. The integral domain is said to be Euclidean domain if there exists a norm n on R such that for any two elements A comma B belongs to R, there exist elements Q comma R belongs to R such that A can be written as QB plus R, where you have the property R equals to 0 or n of R is strictly less than n of B. This is like a division algorithm in numbers or in polynomials, right? So if you have kind of a division structure with a norm associated with which relates the quotient b and the remainder r in such a way, so the divisor b and the quotient r in such a way, then your integral domain R is said to be an Euclidean domain. Okay, so now we'll see some examples. First example is set of all integers is a Euclidean domain since you consider norm n as any integer will go to its modulus. So yeah, with this function is a norm, you know, and with this norm, the whole division algorithm that we do in natural numbers or integers will follow up directly, right? So it is easy to verify that A is an Euclidean domain. Similarly, if you take f be a field, then f over x is a Euclidean domain we write it as short ED, okay, as Euclidean domain with n as n for any polynomial px is your degree of px, right? Again, by the whole division algorithm in polynomials, you get this nice division property we have, and n thing will follow, right? The norm thing. The degree of the remainder is less than the degree of the divisor. This. So these are some examples of Euclidean domains. So what is so special about this Euclidean domains is that it forces every proper ideal to be the principal ideal. Okay. So following proposition follows. Every ideal in a Euclidean domain is principal. Okay. So we'll see the proof. I want to show every ideal is principal. Okay. So let I is an ideal of R, where R is Euclidean domain. If I is 0, then we are done. If I is non-zero, choose. So see, if they are all non-zero, then you consider set of all n of a. A belongs to I minus 0. Okay, so like consider the norms of all non-zero elements in I. Okay, so this will have a minimum element, minimum norm element, right? Right. So choose D such that n of D equals to minimum of A. So this will exist because of the well ordering principle in natural numbers or integers, right? You will have this minimum for this n of A, and then you choose such an A for which n of A is minimum. Okay. So the claim is R is ideal generated by the element D. Okay. So how do we show this? See, I is an ideal and D is an element of I. So basically, this is straightforward. Let R belongs to an element I, or I'll just take A. So what I can do is I can write A as some QD plus R, right, with R equals to 0 or n of R strictly less than n of D, right? But if R is non-zero, this contradicts founded is the fact that n of d is minimum of A, right? Minimum of set of all norms of non-zero elements, right? Since R is non-zero, so this is not possible. Hence, R has to be 0. But then what does this imply? Yeah, here only we can see, but this will imply A will belongs to this, right? Because if R is 0, A equals to Q times D, which A belongs to ideal generated by D, which implies I is ideal generated by D. Right? So we have proved that any ideal I is generated by some element inside it. More precisely, any ideal I will be generated by an element of least norm. Right? So that's all. Hence, basically what this proposition says is every Euclidean domain is a principal ideal domain. I haven't said what principal ideal domain is, but loosely it is an integral domain where every ideal is principal. Okay. So from this proposition we can conclude that so many ideals are not Euclidean domains. Okay, for example, consider the ring as Z over X. Okay, this is polynomials with integer coefficients is not a Euclidean domain. Okay, how did I concluded this? Because Z over X is not a PID. Yeah? I will show that Z over X is not a PID, hence not an ED, because we just showed that ED implies PID. Right? Okay, so consider I, which is set of all polynomials such that P of 0 is even. Okay? Basically, polynomials with even constant term. Okay? Another representation is you can write this as ideal generated by 2 and x. So suppose I is generated by some single polynomial a of x. Okay? For some a of x belongs to integer coefficient. Right? So I ultimately want to show that zx is not generated by a single element. I mean, hence zx is I is not generated by a single element. Hence zx is not a PID. Hence not ED. Suppose this happens. So what do you know is 2 belongs to I, right? Hence belongs to ideal generated by AX, which implies there exists polynomial QX such that 2 is equals to QX times AX. Right? So yeah, so when I define a degree, right? So here uh, yeah, so what do you know here? So degree of QX plus degree of AX should be same as degree of 2, right? Which is 0. Right? Which implies QX and AX both has to be constants, also should belongs to this set, plus minus 2 or plus minus 1. Right? So if A of x is plus minus 1, then ideal generated by A of x is the whole zx, right? But this is not possible because I mean this is I, and this is ideal consisting of all polynomials with even coefficient. Yeah? In zx you can have polynomials without coefficient, of course, right? So this is not possible. If A of x equals to plus minus 2, then basically I will be ideal generated by 2, right? But now do you have x there? That's the question. So x belongs to I, which is same as ideal generated by 2, hence x can be written as 2 times some other polynomial qx, where qx is in zx, right? But this is impossible because Qx is the polynomial integer coefficient. So whatever is the coefficient of x there, you multiply it with 2, it will become an even number, right? But in your left hand side you have x, where the coefficient of x is 1, which is odd. So this is not possible. Hence your assumption was wrong. Hence I is not equals to, right? It means Zx is not a principal ideal domain. By the proposition earlier, it follows that Zx is not PID. Sorry, is not ED. Okay, so see in this Euclidean domains, basically in any natural numbers we have a thing called greatest common divisor, right? Like greatest common divisor of 3 and let's say 6 is 3, or greatest common divisor of 4 and 6 are 2. So we can generalize this concept even in any commutative rings. So how do you define this is as follows. R be a commutative ring with unity. I'll just give a generalization. Let R be a commutative ring and let A comma B belongs to R with B non-zero. So first thing is, you say A is said to be a multiple of B if there exists an element X in R such that A can be written as Bx. Okay, this is the first thing, a multiple thing. Second, a greatest common divisor, a GCD of A and B is a non-zero element D such that following holds. First thing is, of course, it has to be divisor of A and B. And second thing, if D dash is any element divides A and B, then D dash will divide D. Okay, so it is a divisor of both A and B, and it is greatest in the sense of division. Okay, so you take any other divisor that will divide D. This is a definition of greatest common divisor. So how does it relates with this ideals thing is given by in the following proposition. Proposition: if A and B are non-zero elements in the commutative ring R such that, okay, this is a important condition, ideal generated by both, okay, okay, that is this thing, generated of A and B is a principal ideal. First thing is you should have that the ideal generated by two elements is indeed principal ideal generated by, let's say, D, then the element D is the greatest common divisor. Is the GCD of A and B. Okay, so like basically how it goes. Suppose example, consider uh, I is ideal generated by 4 and 6. Okay, what is this? This is set of all elements of this form, right? 6n plus 4n plus 6m, where n comma m are in integers, right? But you know, for any element, you can write 4n plus 6m as 2 times 2n plus 3m, right? So now the question is, can you write any natural number, any integer as 2n plus 3m, right? The answer will be yes, because take any r belongs to integers. R can be written as 2 times some element n if n is odd, if r is odd, even, sorry. Otherwise, it is 2 times n plus 1. R is odd, right? In first case, we are done. In second case, if r is 2n plus 1, what you consider is 2 times n minus 1 plus 2 plus 1, right? Which is simply 2n n minus 1 plus 3. So it is again of this form, right? So any integer is can be written as 2 times 2n plus 3m. So what do you get in conclusion? You get I is same as 2z, right? So this is basically ideal generated by 2, right? So ideal generated by 4 and 6 is a principal ideal indeed generated by 2. Hence 2 is the GCD of 4 and 6. Okay. So generalizing the GCD concept to any commutative rings is in this way. Okay. This proposition will give you a sufficiency. But this is, I mean, not a necessity, but yeah, sufficiency. Because you need the ideal to be what do you say, principal ideal here in this statement. This is not always true. For example, the if you consider ideal generated by 2 and x in z over x, this is not a principal ideal, but they still have greatest common divisor, which is 1. Okay. Now we will see a question. Let R be a Euclidean domain. Okay, you have an Euclidean domain, and let M be the minimum integer in the set of norms of non-zero elements. Okay, that is M is minimum of n of A belongs to R minus 0. Let's say R. So you consider all non-zero elements and then consider their norms. So it will have a minimum element because of the well-ordering principle of natural numbers. And then you could call that element as M. Okay. Now what you have to prove is that every non-zero element of R of norm M is unit. So that if R belongs to R minus 0 such that n of R equals to M, then R is a unit. Okay, so think about this. So how do we show this? I have to show that R is a unit, right? So consider, right? So if I show that this ideal is the whole ring R, then I'm done, right? R will be a unit. Or okay, this should name A. You can write R as A times Q plus remainder R naught, right? With R naught is equals to 0 or n of R naught strictly less than n of A, right? But as we saw earlier, this is not possible since n of A is least, is the minimum of all norms of non-zero elements. This is not possible and this is the only case possible, which implies R equals to A times Q. So what does it means? I equals to whole ring R, right? Which implies 1 belongs to R, 1 belongs to I, which implies the 1 equals to A times Q for some Q in R, right? This implies A is unit. That's all. So what did I show? I showed that in a Euclidean domain, if you consider norms of all non-zero elements and then consider the minimum of all that, then any element with the norm minimum will be a unit. Okay. Example, I mean how this proposition is useful is, consider R to be fx, okay, and n to be, we know this is degree, right? Degree of p. So now what is the m here? Yeah, m is minimum of degrees of px where px is non-zero polynomial, right? This is 1, right? Because constant polynomials of degree 1 and below that there is no degrees, right? So this is 1. So consider any constant polynomial, and you know that any constant polynomial has unit because constant polynomials are basically elements of f, and those are precisely the units in f over x, right? So you can infer that every constant polynomial in fx is a unit by the above proposition, above question. Okay? Yeah. So now there is a second concept which is a kind of a sub concept which is called principal ideal domain. PID. So how is it defined? Definition: a principal ideal domain PID is an integral domain in which every ideal is principal. Okay. So example: is a field. So like basically every field is a principal ideal domain. Like as you know, in field you have only two ideals, singleton 0 or the whole space X, and both are principal, right? Both are singleton 0 is generated by 0 and whole field F is generated by 1, right? This second F over X or field F. Third, because we have already observed that Fx is Euclidean domain, and every Euclidean domain is PID, right? As we have seen. So I can write examples as Euclidean domains, right? Because every Euclidean domain is PID. And counterexample, as we have already noted, Zx is not PID, right? Indeed, and generated by 2 comma x is not principal. Okay, so what is special about this principal ideal domain is the following proposition. It forces every non-zero prime ideal to be a maximal ideal. Okay, so this is the important part. Proposition: every non-zero prime ideal of PID is maximal. Okay, so let's see the proof. So let I is I be a prime ideal, a non-zero prime ideal. Since you are in a PID, I will be generated by some element, let's say A, right? For A is in your PID R. Now suppose I is contained in B. Yeah, so B is in ring R, right? The claim is either ideal generated by B is same as this, or this is the whole ring R, right? Okay. Now since A belongs to ideal generated by B, A will be can be written as B times M, let's say, for some M belongs to R, right? Now since you are in prime ideal, since I is prime, implies B belongs to I or M belongs to I, right? If B belongs to I, then you are done. Then ideal generated by B is same as ideal generated by A. If not, let's say if M belongs to I, then you can write M as some A times N, right? Because I is ideal generated by A. So what do you get? You get A is equals to B times AN. Simply A times BN basically. So this will imply 1 equals to Bn, right? Because you are in an integral domain, right? But this will imply B is a unit, hence ideal generated by B is the whole ring R, right? Okay. So this is done. So I have shown that any ideal which contains I is either the whole ring R or I itself. Hence I is a maximal ideal. Basically, in a PID, every prime ideal is maximal. Right? So, an important corollary of the result is the following. Corollary that if R is commutative ring such that the polynomial ring Rx is a principal ideal domain, then R is a field. Okay, so this is an important corollary. So an application is basically you can directly conclude that ZX is not PID. Why? Because by this proposition, if ZX is a PID, then Z will be a field, right? But Z is not a field, so you can directly cut it out. ZX is not PID. Okay. So how to prove this corollary? Prove. Okay. So yeah, R over X is PID. Which implies basically Rx is an integral domain, right? But we have seen earlier this is if and only if R is integral domain, right? So we have at least this thing that R is an integral domain. So now consider I as ideal generated by X. So since R is an integral domain, I'll write once it is an integral domain, we get R quotient I is uh, okay. First thing, yeah. Since R is an integral domain, so what do you know? R quotient I, which is equals to R, right, is integral domain. Yeah, which implies I is a prime ideal, right? But we know in a PID, every prime ideal is maximal. But since we get I is maximal ideal, hence R quotient I, which is Rx quotient ideal generated by X, which is equals to R, is a field. Okay, this follows by the proposition we have seen very earlier that in a integral domain or commutative ring within unity, R quotient I is maximal if and only if R quotient I is field if and only if I is a maximal ideal, right? So hence every argument follows. This is an important corollary. So now we'll see a question. This will show that prove that quotient of a PID by a prime ideal is again a PID. Just give me a minute. Yeah, so what do you have to prove? The quotient of a PID by a prime ideal is again PID. Okay. Proof. Let R be a principal ideal domain and I, subset of R, be a prime ideal. This implies I is a maximal ideal by the earlier proposition. Hence, R quotient I is a field. Right? So like, yeah, there are two conditions. In first condition, this is I is non-zero. Okay. So in that case, R quotient I is a field, is a non-zero prime ideal, hence a maximal ideal, hence is a field, which implies R quotient I is PID, since every field is a principal ideal domain. Second case, if I is 0, then basically R quotient I is same as R, right? Hence, R quotient I is a PID, right? So in any of the case, you quotient of a PID by a principal ideal is again a principal ideal. So the statement follows. Yeah. Okay. So now this is done for the week 5. If you have any questions, you can ask in the portal. Thank you for your attention.